A reinforced thermosetting resin is a composite material that is equally suited to small or large production runs. When only a small number of units is required, as with these boats or the moulds from which they are made, or for this prototype car, then hand laminating of composite materials into a mould is the most appropriate method of manufacture. Even though this process of hand laminating is very labour intensive, there is an overall cost saving because the equipment used is simple and cheap. When working with composite materials, it is recommended to wear safety glasses at all times, especially when handling or mixing chemicals or using power equipment. The process starts with the application of a release agent to the surface of the mould, in this case a wax. The better the surface of the mould, the better the finish on the final product. The moulds are generally made from composites having been formed over a pattern that is the shape of the final product. After a final polish of the surface, release agents are applied. This is often in the form of a polyvinyl alcohol, which increases the ease with which a part can be removed from the mould, as it ensures that the gel coat does not stick to the mould surface. The PVA release agent dries within 15 minutes. A gel coat is then applied to the mould surface. It is a thermosetting polyester resin that has been blended with fillers and colorants. This is carefully weighed so that the correct amount of catalyst can be added to obtain the required curing time for a specific application. This time may vary between 15 minutes and 2 hours. The gel coat gives the cosmetic finish to the component, providing color and texture. The gel coat can be sprayed or hand painted onto the mould, and for this reason is available in various viscosities. It is important that the gel coat be applied evenly, as an uneven gel coat can cause various cosmetic faults, such as shrinkage or pre-release. The amount of chopped strand mat and woven roving reinforcement required is calculated, cut to size and weighed, so that the correct amount of resin can be prepared. A precise amount of catalyst is added to the previously weighed resin. Methylethyl ketone peroxide catalyst is commonly used where the resin is required to cure at room temperature. If, however, the part is to be made using elevated temperature moulding technique, a different organic peroxide catalyst is used. This is stable at room temperature, thus ensuring that the cross-linking of the molecules in the resin does not occur until the catalyst is activated by the heat of the mould. Aiming at a resin-to-glass ratio of 2:1, the first layer of chopped strand mat is wet out. This mat is relatively inexpensive and is easily moulded into a three-dimensional shape. Rolling removes any entrapped air and helps compact the fibres to ensure a fault-free product is produced. Another layer of chopped glass mat is added, wet out and rolled as before. These multiple layers will increase thickness and strength of the final product. Finally, a layer of woven roving is added to improve impact strength and also to add bulk to increase stiffness. Woven glass cloths impart a greater strength to a composite structure than chopped strand mat, but they are generally more difficult to form into compound shapes. After approximately 5 hours of curing, depending on the ambient temperature, the sheet is strong enough to be demoulded. With hand laminating, a first-class product can be produced with minimum equipment. There are three main groups of fibres used for reinforcement in composite materials. Glass fibre, aramid, an example of which is Kevlar, and carbon fibre, which is available in a range of strengths and stiffnesses. They are used in three common forms: chopped strand mat, almost exclusively fiberglass, woven cloth, or unidirectional material. Steel is 3 to 4 times stronger than chopped strand mat and is of a similar strength to woven glass or carbon, but weaker than an aramid. However, when these fibres are used unidirectionally, they are 3 times stronger than steel. If, however, these materials are compared to steel on the basis of specific strength, that is, strength divided by density, they are much stronger. In the case of unidirectional aramid fibre, 22 times stronger per kilogram than steel, and even glass chopped strand mat on this basis is stronger than steel. The other property that is very important for structures is tensile modulus, which is a measure of stiffness, and in this, steel is well ahead of any of the composites. Faring by far the worst in this comparison is chopped strand mat with a modulus of 8 compared with steel at 207. But when relative densities are taken into account, then carbon fibre materials have outstanding specific stiffness. If the strength of a material is plotted between 0 and 90 degrees, the strength of chopped strand mat is the same in all directions. Its strength is low because of the high percentage of resin, up to 70%. It is the fibres that give the composite its strength. For fibre content between 10 and 60%, the higher the fibre content, the stronger and stiffer the material. If the strength for a bidirectional woven cloth is plotted, there will be a dip in strength at 45 degrees, as there are no fibres in this direction. If another layer is added, such that its fibres are at 45 and minus 45 degrees, then its maximum strength will be less due to increased section, but will be the same in all directions. If all the fibres are aligned in the one direction, then the strength in that direction will be more than twice that of the bidirectional woven cloth. It will have very poor strength in all other directions. If stiffness instead of strength were plotted, the graphs would be very similar. Aurora, a car powered by the sun, is potentially the fastest solar car in the world. Its 3 wheels are tied together by a triangular frame that needs to be light and exceptionally rigid. For these reasons, a carbon fibre material was selected. To keep this quality catamaran hull to an affordable price, it is made using relatively low-cost glass cloth. Where very high loads are to be distributed through the structure, woven Kevlar is added. A daily quota of 25 truck bonnets is required. This will entail the laying up of 2 tons of composite material. The polished waxed surface of the mould is generally sufficient for the easy release of the bonnet from the mould. But if there is any difficulty, a release agent is applied to the surface. The bonnet is of such a shape that it cannot be removed from a single piece mould. To overcome this difficulty, the mould is made in sections that are bolted together. When moulding is complete, the mould is disassembled to allow the bonnet to be removed. In the modern composites industry, the safety of the worker is paramount. Boiler suit cuffs are taped tight at the wrists. 2 pairs of gloves are worn. The outer rubber pair is a barrier to glass and resin, and a cotton pair for extra comfort and to absorb perspiration. A head shield and face mask are put on. The overspray from the gel coat is extracted by strong exhaust fans at the back of the spray booth, leaving the operator in clean upstream air. For extra strength, reinforcing pieces of chopped strand mat are laid up on the gel coat. The glass reinforcement is rolled out to ensure compaction and complete wetting of the fibres. The first layer of chopped roving and resin is applied. An airless spray gun is used. The resin and catalyst are mixed within the gun and then hydraulically atomized. The airless spray reduces styrene emissions, thereby improving the working environment. The resin spray carries the chopped glass onto the mould surface with minimum air entrapment. It is rolled out. A 30% glass content is achieved by this process. A second layer of glass and resin is applied. This gives a wall thickness of 3 mm. For added stiffness, a 3 mm layer of core mat is added where required. This is generally on the flat areas of the bonnet. Over this core mat, another layer of chopped glass is sprayed. The thickness of the laminate is measured using a comb gauge of varying tooth length. Each tooth is calibrated in a gradient, and when the comb gauge is pushed into the wet laminate, the operator can read the thickness. Additional preformed fiberglass pieces are added to the bonnet, increasing overall strength and stiffness. A final layer of glass and resin is sprayed on to combine these additional pieces into the structure. With the aid of wedges and compressed air, the bonnet is split from the mould and the cycle starts again. To speed up the curing process after demoulding, the components are baked at 70 degrees Celsius for 2 hours. This post-curing ensures that the parts are fully stabilized. At ambient temperature, the parts can take 7 days to be fully cured. The use of sprayed chopped roving is a very efficient method of producing large components on a production basis. A polyester resin glass fibre composite was selected for the construction of the Australian Huon-class mine hunter, and this allows for a very low magnetic and acoustic signature, essential for the task the ship has to carry out. The single-skin monocoque hull will never rust or rot, and is built to withstand very high shock loadings. The ship is made up of 24 separate sections. The hull is moulded in one section, and when complete weighs 150 tons. The fuel and water tanks are made such that they are an integral part of the ship's structure and contribute to its strength. The decking and superstructure is made alongside the hull, and then assembled and bonded together, a very efficient method of manufacture. It is not uncommon to laminate up to 2 tons of material a day. One of the main advantages of composites is that the strength can be put just where it is needed. For example, the bottom of the hull is made up of 84 layers of woven rovings, giving a thickness of 160 millimeters. This reduces to a thickness of 50 millimeters topsides, made up of 28 layers. The glass to resin ratio is 1:1. The steel mould is made in sections, so that when the hull is complete, the mould can be disassembled, leaving the hull free-standing. Also included in the mould structure is a very extensive fume extraction system. The resin-impregnated glass is draped from one side of the hull to the other. Halfway along the hull, a pyramid of layers of glass is built up. This is then added to, working simultaneously towards bow and stern. This leads to an overlapping structure like bricks in a wall. Heavy rolls of woven roving, 1.4 kilograms per square metre, are fed through a purpose-built resin-impregnating machine that delivers the exact glass-to-resin ratio with the appropriate amount of catalyst for the sections being laid up and the temperature of the day, so that curing will take place at the correct pace. In the production of these catamaran hulls, vacuum bagging is used. This process is a modification of open mould forming, where the glass and resin may be laid up by hand or be introduced as pre-impregnated sheets. Vacuum bagging is used to produce products of exceptional quality or complexity. Each hull is made up of over 100 different pieces of reinforcing material. After the gel coat has been applied and has cured, the first layer of glass cloth is laid up. A vinyl ester resin is used to increase strength and toughness. Making sure of 100% penetration, the resin is forced through the glass. The excess resin is then removed, so as to obtain the maximum fibre to resin ratio. There must be close attention to detail if you are going to produce yachts that are the best in their class. For high strength and toughness, Kevlar is used in combination with rigid PVC foam and fiberglass cloth to produce a lightweight, rigid sandwich structure. If some of the fiberglass in the hull was replaced with carbon fibre, a stronger, more rigid hull would be produced. However, the cost would be a lot higher, and it is for this reason that carbon fibre is excluded from some yacht classes. Peel ply, which is later removed, gives a surface roughness that will help ensure excellent bonding when other parts are added to these sections. A perforated plastic film gives a good internal surface finish. Perforations allow the excess resin to move through and be soaked up by the bleeder fabric, which, after debagging, is stripped off and thrown away, thus removing the excess resin. The bleeder fabric also serves to evenly distribute the vacuum across the job. A vacuum bag is slid over the half hull and made airtight. A vacuum is applied, and the 45 different parts in the half hull are squeezed together and cure, thus forming a structure of high integrity. When curing is complete, approximately 1 day, the vacuum bag, bleeder fabric, perforated film and peel ply are removed. 2 halves are bonded together with more resin and glass, and when this is cured, the complete hull is stripped from the mould. The completed hulls now require trimming and detailing before final assembly of the yacht. This is the tail rudder of a modern airliner. These rudders are to be produced at the rate of 7 a month. They must have high strength and rigidity and be structurally perfect. The method of production used is vacuum bagging of carbon fibre prepregs. This electroformed nickel tool is used in the making of a part for the leading edge of the rudder. The blue layer is a surface film sheet, over which the first epoxy resin impregnated carbon fibre cloth, called a prepreg, is laid up. Around the edge, glass breather tape is put down. This is not part of the final product, but is there to act as a passageway along which air can move when the vacuum bag is applied. A template is used to mark the position for the placing of the next piece. Exactly the same technique is used for the marking out of the rudder skin. A layer of epoxy adhesive is laid in to bond the core material to the carbon fibre skins. The core material is used to increase section thickness and rigidity of the part. A second layer of adhesive film. There are 20 separate pieces to make this part, and 5 times during the layup process the pieces are vacuum bagged to ensure complete compaction of the layers. More plies of carbon fibre prepreg are added. To help shape the prepreg over the core, warm air is used to soften the resin. Cores are extensively used in the construction of the rudder skin. For simple shapes, the phenolic resin bonded paper honeycomb core material is cut in a bandsaw and then sanded. Production of complex three-dimensional cores, a computer numerically controlled, that is CNC machine, is used. To minimize the amount of expensive scrap, the shapes to be cut from carbon fibre prepregs are nested. The cutter path is determined. A CNC control cutter blade cuts the sheet. The cutter blade moves up and down, accurately cutting out each individual piece. Pieces are collected into kits for each individual part to be made. All 20 pieces have now been laid up, and a final layer of Tedlar, a thermoplastic material, is added. This will bond to the epoxy resin and form the inside surface of the part, acting as a protective film. The final bagging. The release film with its tiny holes is in place, and over this a breather cloth allowing the air to escape. And finally, the nylon vacuum bag is sealed to the tool face. Fittings for the vacuum line are added. The vacuum is applied. The assembly is now ready for curing in the autoclave. The longest autoclave in the plant is 15 metres long and 4 metres in diameter. Thermocouples are also connected to closely monitor the temperature of the parts. The parts are heated to 180 degrees Celsius and held for 2 hours. The complete heating and cooling cycle takes approximately 6 hours. Some of the tools used cost up to $1 million each. They are very precise pieces of equipment. The tape is removed and the parts easily lifted off the tool. With the aid of a jig, the smaller parts are drilled and trimmed to size. The finished parts are non-destructively tested. A large skin by through transmission ultrasonics. The sound waves are transmitted through the top and bottom water jets. If there is a defect in the part, the pulse is partially absorbed. The results are displayed on a screen or they can be printed out. For small curved parts, a single water jet column is used. When a defect is found, an alarm sounds. For other parts, a reflecting ultrasonic test system is used, where the sound waves bounce back off the bottom surface of the part. All 70 separate pieces in this rudder must pass through such quality control tests before final assembly occurs. A simple-looking rudder is in fact a very complex assembly.